Hello, gentle readers. It's February 13th, 2024, and this afternoon I thought I would take a look at here for moment and motion. Basically about this question: meters per second or seconds per meter? So anyways, today what it is just kind of a usual day, and there's nothing particularly extraordinary about it, yet in time, as if for every moment, there's always this motion. Everything's distinct, everything's unique. There never really is anything that is the same sound twice, or lightning as it strikes, or any of these kinds of things. While yet in the same, it's all a cohesive and coherent whole, a continuum of the things. Very much so. So what I hope to do today was to discuss this idea of meters per second or seconds per meter, because we have a very usual sort of development of how you keep track of things in terms of their velocity is displacement over time. And the units of displacement are meters, and the units of time are seconds. So trying to figure that out is then as well that you can also kind of track it in terms of their ratio and the reciprocal or inverse as whether it's seconds per meter. Just like any kind of other usual sort of ratio in reverse. What is it that it so results that it's one way or the other, which one is privileged in a sense? So in the theory, that gets into what's absolute and relative. And then as well, we have as regards what's fixed and free, and also what's regards to near and far. These sorts of descriptive terms expressing either side of these complementary duals gets into why the regular and the ordinary and the rulal and the obvious is framed out this way, and with a fixed point to some fixed point. This is generally the entire classical milieu of our mesoscale, that the mesoscale is what's in the middle, where we all inhabit. And then that from any particular observer's point of view, that two observers see the same things from each from their own perspective. So whether seconds per meter or meters per second is kind of decided, because it's meters per second in the usual sense that everything is according to these seconds, and that the seconds are these sort of uniform changes for everybody and everything. In the theory, here's dynamical modeling, or is according to being parameterized by time. The time is kind of how things are so phrased and framed. And so that's why it is the one way or the other. But the other way is just as apropos when it's when things are as of they part, or as they meet. You usually would consider this in terms of the stopping distance vis-a-vis time to 60 or something like that. These being usual bounds in what results the guarantees of issues in related rates problems, or getting on the highway, or coming to a complete stop, and these kinds of things. Now, in the descriptive differential dynamics, this is really kind of pulled together and called this stop derivative. So the stop derivative is this kind of idea that what happens is that you got meters per second, and then you got meters per second squared is acceleration, meters per second per second. What's the difference in the velocity in any given time period? And so what's that? Meters per second per second. Higher order acceleration. Meters per second per second per second. Higher order acceleration. Meters per second per second per second. Higher order acceleration. So in all the infinitely many degrees of something just has a gentle push, and it's just a simple linear impulse, and it goes from a velocity from 0 to 1, and kind of that instant. Well, in that instant, it piled and tumbled over infinitely many degrees of freedom to arrive at this derivation. So maybe degrees of freedom wasn't really the proper term here, because it's degrees of derivation, degrees of fixedness together. With regards to the linear impulse and the classical, all the infinitely many higher order of acceleration, any one of which is non-zero, and as time, as it's infinitely divisible, gets smaller and smaller and smaller and smaller and smaller to an instant, that these are the kinds of ideas that go into framing this whole thing. So you got meters per second, and then you got seconds per meter, or seconds per meter per second. As you can see, you can kind of frame these quantities relating to each other, that they're in ratio and constant form and proportion, which is the great thing that really is kind of what geometry is for, and the congruency. And here that the sum of the angles is the angle of the sum, and the converse holds. But the angle of the sum is the sum of the angles. They're mutually modeling each other. They're equity interpretable either way, which result their products. These are the kinds of things that get into the things. So for physics, then there's this, what you would call absolute and relative. So for different observers, the most key thing that people know about is the Doppler effect. And so the Doppler effect basically defines for waves that a moving source of waves of a constant wavelength and frequency will, as it moves relative to the observer, cause the increase of the frequency and the lowering of the frequency, the Doppler effect. So the Doppler effect is probably the most usual feature in dynamics that shows up in these relations of the waves and how things are like so. And so that's something I hope to get into today and try to mostly, in a sense, bring for myself some kind of idea how to continue to extend this sort of stop derivative and these notions that go into making for real analytical character of these infinite dimensional superclassical notions, because I think that in the non-standard, such as it is, that is where all the great wealth of opportunity lays, because the classical is very well explored. And then what's not very well explored in it usually is that it is incomplete. As we learn all these things in school, the formalisms vis-a-vis the very nature of the experience of things, the practical application of the control of walking up and down the stairs, or anything even so simple as that, vis-a-vis the theory of the walking up and down the stairs, are two different things. And so in one sense, the theory has it's got its opinion, and as we talked about, it's got its entire theoretical opinion, and then it's got its entire empirical applications as well, all part of the theory. It's a scientific theory. It's got empirical setting. It's got a theoretical setting, and including one that's purely theoretical. Vis-a-vis then in the practical, it's not always really easy to say. Even if our eyes see not spherical images, how our sense of perspective and projection so meet. Or things like, does anybody even see the same colors at all? Or do we just have the same words for what we each see differently? These are the kinds of things that help establish the dialectic for the domain of the superclassical and the richer dialectic of complementary duals and the dual infinite consistency, these kinds of things, in a dualist monism. The other day I was talking to somebody and we got talking about Zeno's motion, and it's like, stop, don't stop, and all this kinds of stuff. How can it be that ad absurdam, that it results that the tortoise and the Achilles do observe each other in passing each other? How can it be that the arrow reaches its target and it either only goes half, and again, that the sum of the angles is the angle of the sum, or that the sum of the halves is the sum of the halves. Whether it arrives or not. Ad absurdum then is for ab absurdum. Into, out of. These are the kinds of things that help reflect that there are these complementary duals to then, after there's the classical exposition and setting of all the things, that there results this fuller paleoclassical sort of approach to numbers, geometry, infinity, continuity, and then all the things that go into what for physics is a gauge theory, a unified field theory, a continuum mechanics, a differential system, and all these other things that supposedly make for the desiderata and requirements of foundations of mathematics and physics. So that's just fun. Looking at some books, see, now these first two books here are from Curme. This is a grammar of the English language, and by a grammar of the English language, what it has is it has all the parts of speech. It has the accidents, which is, when you hear accident, you think of an importune, unintended event, an accident. But what accidents means really is the ordering of events. It's just like, well, it's what happened in what order. So as far as grammar goes in the parts of speech, accidents, D-E-N-C-E, is its own kind of thing with regards to when you say words in a given order, how they relate to each other according to the syntax and the grammar. And then also it's got kind of a bunch of examples. Now, so this is from like 1920 or something like that, or even earlier, because it kind of follows things like the project of the Wortbuch. This is, can you imagine, it's a dictionary with all the languages in the world in one book. And so this, though, is copyright 1935, and Curme here, he's an American, and so this is a lot, or at least it covers American English besides British English. And so compared to something like today, they'll have like the Cambridge, parts of speech and grammar and all this kind of stuff that we have. Basically, when we learn to diagram sentences for grammar, we use Tesniere or something like that, if I'm not mistaken. And so in the computer syntax and computer grammar, or the formal approaches these things, there's kind of two really different sorts of formal approaches. And so one is what the computer scientists use, and this is Noam Chomsky's categories of grammars according to the context, and insofar as whether it can just read forward and it's right linear, or whether it has context that it needs to establish that it has different syntaxes and bracketing and grouping, and otherwise how mechanically, with the very least amount of resources, the reader moves forward and can spew out these tokens that then get assembled to make an abstract syntax tree. So that kind of sentence diagram is not what you think of when you think of natural language, grammar, parsing, making syntax diagrams, reflecting according to the parts of speech, the words, the relations, according to the copulas in the middle, what they is and are. They're two totally different things about the same thing. So this is one where when I'm studying and trying to figure out how to make it so that I could write programs that can digest, to parse, all about parse and the natural language, it's got to be framed in terms of how people use language, not just so much as like, this is the easiest, fastest thing. Going back to the old idea of pick 2 out of 3. Cheap, fast, and right. I'm more interested in the right. I'm even willing to give up the other 2 for that. So, for correct. Yeah, I got one of these books down in Portland at Powell's Books, and then I wanted the other one, so someone found it for me. I was able to get it ordered. There we go. So those are interesting. They detail all the parts of speech. And it's a very full treatment of English grammar and syntax. Well, these here, I've been just kind of repiling these. This is differential and integral calculus, or Courant. And so when I leafed through these before and looked through them only briefly, but I did pretty much scan through them. And what I'm curious about it is mostly about the identity dimension and the stop derivative, because what I want to do is relate it to then with regards to the integral equations and the differential equations, those being two kind of complements to each other, complementary duals, with regards to how differential equations, solutions are integral equations, and integral equations, plane curves are differential equations. And that they mostly kind of are reflective and symmetrical about that, but there are ways to think about that they are not. That is the key thing, filling out the fuller picture, the fuller diagram, the fuller complement, to have it like so. And so this gets into some things recently. I've been looking at continuous topology and continuous domains, because mathematics is kind of built up from the complete ordered field and the infinite divisibility and delta epsilonics, which is great. But the whole idea of like between 0 and 1, it goes from 0 to 1, empty to full. It's like, well, that's kind of a different way altogether, because it would have 0 and then something next to it. So that's not infinitely divisible. So just don't even say that, leave it out. We're going to have a special class before 10th grade in calculus. We'll call it pre-calculus, where we explain how the limit is built with delta epsilonics, because, it's like this. It's like 0.999 and 1.0. It's like they're the same this way, because that way everything's kind of a little bit before, but everything after that for at least 5 or 7 years of education is all assuming it's just this one way. So without having to, have 2 classes for everybody or something like that, we're just going to keep this all in the linear narrative and curriculum, that these are continuous domains. You got 0 to 1 only, and they're line rails, and then you have the complete ordered field, they're field rails. And then the signal rails is like, if you have a wave, like you can think of anything in between any 2 bounds as a wave somehow, then it's just like, well, if you have double that, then you can take that off and put it back, and then you'll have enough information to recreate that. They're the signal rails. So there's at least 3 kinds of these notions of continuous domains. After the integer continuum, the whole numbers, from the long line, the continuum, all the expressions of real valued formulas. So from like this least and sparsest to this most and densest. In the middle, these field reals, that the integer and their non-integer parts is these line reals, and then coming down from the long line is these signal reals, and they all fit into one replete setting. So then the idea for the subfield that's called topology is that, well, we have some of these results that end up being in function theory, as we talked about here. And then some things will have results field as topology, where function theory is how things are relate from the domain to the range, from left-hand side to right-hand side. And topology is how things relate in their proximity, their nearness, their neighborliness here. It's basically defining this continuous topology and continuous domains in terms of the neighborliness, and the functions defined in terms of their Cartesianness. That this all together helps make a quite more digestible thing that fits pretty much, in a class before calculus. So that then people would feel like, it's like, yeah, we're going to follow these results on in, instead of being told, hey, there's 0.99 or 1.0. There's no 2 ways to look at it. It's like, well, it's a notation. There's a notation where one it's less and the other one it's equal. These days, a recent survey had that half the students in a class, when asked about 0.999 and 1, had it either way. It's both ways. So anyways, that's just kind of from reading a comment about the accumulation points for theorems on continuous functions. Because today it's just like, hey, as long as we've got continuous functions, then all our functional analysis pretty much lives after this definition of C empty, class of functions that are infinitely differentiable and they're continuous functions. So, Courant, and then looking some more in the Courant here, what I'd like to do is, again, figured out how it is so that the he gets into multivariate and like these accumulation points, the critical points, for the limit points, critical points and accumulation points in higher dimensions in these continuous domains, and with a continuous topology, which is a very particular sort of topology that is both initial and final, and with the notion of contiguity inside continuity. That here he gets into motion and differential equations for motion, the potential of attracting charges. So that's cool when you had something about potential. I'll be curious to look at that just for a moment. Because the idea is that those are the kinds of singular situations that make it so that there's a way to, given a particular fixed things otherwise, that's able to observe what's the free side of that which is with its least action and this kind of stuff. .468. Phi equals const. Big phi or phi. As an extension of the cases considered previously, we now take mu as a positive or negative mass or charge. Negative masses do not enter into the ordinary Newtonian law of attraction, but they do occur in the theory of electricity, where mass is replaced by electric charge, and we distinguish between positive and negative electricity. Coulomb's law of attracting charges has the same form as the law of attraction of mechanical masses. If a charge mu is concentrated at a single point of space with coordinates epsilon, eta, gamma, we call the expression mu over r, where r equals root of this quantity, x minus eta, y minus eta, or x minus epsilon, y minus eta, z minus gamma, those quantities each squared, the root of that. So the root of the sum of the differences of the squares, or rather the squares of the differences. The potential dagger of this mass at the point xyz. So here it's built up about the quadrature, and it's very much related to the Laplacian, and it's kind of so for these partials that makes the Laplacian, which is the second order partials being zero. By adding up a number of such potentials for different sources or poles, each of these sub I we obtain as before from page 283 the potential of a system of particles being the sum of the mu i's over the r i's. The corresponding fields of force are given by the expression F equals gamma grad phi, where gamma is a constant independent of the masses and of their positions. If the masses, instead of being concentrated at single points or sources, are distributed with density mu epsilon eta gamma over a definite portion r of epsilon eta gamma space, we have already taken the potential of this mass distribution to be big phi equals the triple integral of mu over r in the differentials of each of this epsilon eta and gamma. So this is just a way of writing. It's like it's the sum of each. If the masses are distributed over a surface S with surface density mu, then the surface integral, the double integral of mu and u gamma v over r d sigma taken over the surface S with surface element d sigma represents the potential of the surface if the surface is given parametrically by u and v as parameters. For the potential of a mass distributed along a curve, we likewise obtain an expression of the form the integral of mu s over r ds, where s is the length of the arc on this curve, mu of s the linear density of the mass, and r the distance of the point xyz from the point s on the curve. For every such potential, the surfaces phi equals const represent the equipotential surfaces or level surfaces. So the equipotential is a great kind of idea, because then it's with the least amount of mechanical advantage, it's possible to define things to go either way. So it's like there's always an equipotential in carrying a path, whether it's to the left or right. These are the kinds of things that result then for this idea. Otherwise, is like, you know, these are the level lines where walking along the hill is neither uphill or downhill, just like isoclines, just like these other notions of the plane curves in this one. that for this notions of the surfaces with their potential and the volumes with their potential and the line elements with their potential, all for least action, what happens when things fall. Naturally, they so kind of proceed in their tendencies and propensities for the dissipative and attenuative, after the oscillative and restitutive, these usual ideas that are in all these source talks here, that this is a pretty great little thing to help relate this. Now, where it is so that it's kind of like, well, that's, for example, for the idea that this conditions for flow to occur. And so it's on the surface, according to potential, stuff will transit the boundary or not. Then the idea also for this meters per second and seconds per meter bit then is to figure out an idea how to make that. It's like, well, yeah, that's just right, sum it up, and it's those together. Solving it is your own problem, but at least you can write it in this form that it's an integral. So whatever it is that goes into this, it must be that variable in those few terms. Vis-a-vis solving it and finding those other way that you can hold that this variable in these few terms are so the constraint or the limit case or the classical case. So these are the kinds of things to kind of figure out from not so much how to get even less with all of it. So it talks about, just leafing back to this page 268, it's talking about infinite regions of integration. Oh, Cavalieri's principle. So Cavalieri was about the time of Galileo, as we were reading about a little while. He is one of the first guys to solve things in the infinitely fine, the infinitesimal, and the very, very fine. The resolution of this integral into an integral, and he talks about the order of integration. So he's got the integral in dz of the double integral in dx dy, expresses Cavalieri's principle, known to us from elementary geometry, according to which the volume of a solid is determined if we know the area of every plane cross-section which is perpendicular to a definite line, say the z-axis. The general expression given above, the volume of a three-dimensional region at once enables us to find various formulae for calculating volumes. For this purpose, we have only to introduce new independent variables into the integral instead of x, y, z. So that's pretty amusing, because it just helps express that all the higher order language of mathematics, a lot of its goal is just write it in the briefest, simplest possible way. And then that it results when all those things are satisfied, then you know that it's basically mathematically, according to that, the solution of these things. Or a problem, which is then something to find. Arcs in the close. So Courant here is great. I mean, this is mathematics. There's nothing wrong with it. This is 100 years old. Same today. All right. Then these are what we looked at last time, and especially about the singular integrals and nares. We got into a discussion of the convolutional setting and why that just makes for another realm of the applied for the operator calculus, and then what it gets into with things like the Banach space and the Hilbert space with regards then to things like this stop derivative and stuff, figuring out which spaces those kinds of things live in, or just kind of drawing a line through it and say it's going to look like this in this space and that in that space. So you won't really have to care what's going on in the all the tension and potential this spring unleashed to make the slinky piling down the stairs, stair after stair after stair. It's slinky because it'll have been written in terms of just this very regular sort of ideas of beginnings and endings of things. Then it's geometric aspects of the Einstein equations and integrable systems. That is this is a bunch of stuff that is big in the field today. So like we got in the Hamilton-Jacobi equations. Why? Well, what's the Hamiltonian? It's like it's a model of translation of some tensorial products in an eigensystem according to time. It's like, well, what's that with Jacobi? It's like, well, it's better because otherwise there's these skew cases which leave the other one broken. And it's like, well, what does that mean? Well, it's since about 25 years ago when this was written, and since then, it's state of the art. And then the idea that above that is that it's Lagrangians. It's got to be Lagrangians. And then that ends up being just kind of this harmonics and potential theory. And then above that is this real theory of some potentials somehow. And that's kind of how it is, that the state of the art is the state of the art. Sometimes theoretical physicists have a lot of advantages. Why? Because they've worked it out economically that they don't have to really do anything with what happens. The whole idea is just to kind of like either learn how things work and be able to explain things about like the single vortex filament, the relativistic string in a constant external field, one soliton, and these kinds of things with respect to how the antennas of cell phones work, how GPS works in satellites in the sky, how rockets take off and land, how airplanes take off and land, how rubber meets the road, all these sorts of things of the practical, mechanical, and applied, which demand the same sort of thing. Anyways, this has it's got an image of a diagram of the Beltrami's pseudosphere. So the pseudosphere is something I want to mention about space inversion. So the space inversion came up in this talk earlier about Wertheimer and the space inversion and the 2 pi, a full turn all the way around any closed curve. And the idea was the inversion. It was like, well, I was reading this book, and it's a great little book. It's called Elie Mayor's, M-A-O-R, Mayor and Jost. Mayor is a mathematician, and Jost is an artist, and together they put together this book called Beautiful Geometry. And it's a great little book. It's very elementary. It's a great little coffee table book. It gets into stuff like the Pythagorean theorem and E and pi and the golden mean phi and all these kinds of things. Whereas, well, it also leads into the higher order notions, the fundamental theorem of arithmetic, unique prime factorization. It's got a bunch of stuff in one little book. So one thing about that, kind of when there was discussion of curvature and like, is it R? Is it 1 over R? Which one is relevant? Well, it varies, and that's kind of the way it is. But he had a great diagram showing a circle, and so you think of a circle and think of any radius through the circle. So you mark a point on that radius through the circle. And so that's a given portion of the radius. And so you just kind of reflect that to the outside of the circle. So then the closer something gets to the origin, the farther away it is out on this at the end of this projected ray out of the radius. And so that's really cool for these kinds of things about the space inversion, because it basically helps us show that when we're dealing with a classical, when you say something's got 0 meters per second, its velocity is 0. So it's at rest. The entire idea, is there anything at rest? It's like, well, no, it's just that its velocity is 0. So then when you want to invert that, that's infinity. And it's like, well, that's the entire point is why we have that be 0, because infinity is apeiron. It's not tractable, but it's still the same thing. It's still either side of this reflection. So then here the idea is that for this meters per second, when that's 0, and then it's like how many seconds per meter? It's like infinity. And so when does it make for when something's going away from a stop or coming to a stop or rest? When does it make sense to kind of frame things in terms of what goes to 0 either way? Because then that way you can say that it's reached 0 and it's got an equilibrium and a balance vis-a-vis like infinity the long way around. Infinity, infinity, infinity. These are the things to get into the very simple ideas of the classical and the potential for units, dimensional analysis, meaning assign units to these dimensions and the quantities are each attached to the units in their dimensions, which is totally commonplace and ubiquitous in all mathematical models of physical systems. What's the meter stick? This kind of stuff. That then as well, when getting into trying to figure out, is like, well, how are we going to make a mathematics that's able to tumble and turn over these things that otherwise, as a straight line would go through? Is like, I have no conception of reaching this inversion of the space that I have just gone through, is to box and frame this in window and box it and make it so that it's kind of like so. Complementary duals and the usual generalized inverse is about the most cool thing. So Beltrami and Dini, Beltrami's pseudosphere, a Euclidean carrier of non-Euclidean geometry. So we think about it as just torsions or warp or space curves or what. The secret of pseudospherical surfaces, asymptotic coordinates, LHS are Chebyshev coordinates, RHS, CL and AL are curvature lines and asymptotic lines respectively. So we got this classical linear, and then we have the nonlinear, the highly nonlinear, and the asymptotic with respect to each other being the opposite. So this is from a paper that is pretty cool. It introduces words like the helicoid for the helical, that which spirals, stereographic projection. Now maybe we'd have to think about like monographic projection, multigraphic projection, pan and polygraphic projection. The generalized Bianchi-Baecklund map. So Bianchi and Baecklund, especially Baecklund, B-A umlaut, or B-A-E-C-K-L-U-N-D. Baecklund is big. Here we go. Method of generalized Bianchi-Baecklund. Section 2. In the orthodox inverse method, it is assumed that Q goes to 0 when x to 1 goes to plus minus infinity. See, that's how they do it. It's about 1, 0, and infinity, and the treating stuff like 0 when you can't treat it like infinity. However, the method remains valid for an arbitrary background solution, Qx to the alpha. For instance, Q can be periodic or quasi-periodic solution as well. So this just helps to reflect upon that the classical is great, but when you get into Bianchi-Baecklund and Darboux-Baecklund, D-A-R-B-O-U-X, Darboux, that there's quite a bit going on. So this is about the soliton manifolds, kind of a contradiction in terms. The soliton is like the wave packet, the impulse. What is it? So results that comes into or out of as a line in the classical. Whereas the manifold is like in it, in the space. It's pretty great. See, it says isometric, the induced metric. Those being two different words. It talks about usual linear developments with the linear independence and that which goes to make the notions of the vector space. A real semi-simple Lie algebra. These are things about the electrodynamics of extended objects. Einstein's great papers, the electrodynamics of moving bodies. And today here he's talking about when they're not just corpuscular, but extended. Invertible mappings. This is a great sort of paper all through the middle of this book. In the theoretical physics, the classical field theoretic model consists of two ingredients. One, dynamical fields, usually a set of real functions, and two, a Lagrangian density, which codes the dynamics of the model given by the corresponding Euler-Lagrange. Here we propose a concept of bi-invariant nonlinear models, which is a straightforward geometrization of classical field theoretic models. See, here he's just trying to pull it up into this greater space. So these are the kinds of things that go into the requirements and desiderata of a fuller field theory. So this is one of the greater extended sections in this collection. And it's cool because he both gives things direct, clear, and simple prose descriptions, and as well definitions, and then the use of the language of the things, and then the graphically and abstractly symbolically the variables in the expressions of formulas and equations, and the definition of structures linearly as linearly, that this entire linear narrative is really pretty cool. And it says part of this is part one of the why solitons in geometry, and he quotes George Lamb, that this is a pretty good thing here. Soliton surfaces and their applications. Soliton geometry from spectral problems. Anthony Sim, SYM. Institute of Theoretical Physics, Warsaw University, Warsaw, Poland. This paper contains a complete presentation of the ideas and results of the approach of soliton surfaces, manifolds. In this approach, any n-dimensional soliton system with a matrix real semi-simple Lie algebra G possesses its own geometry of n dimensions, submanifolds of G. Various applications of this approach are discussed. The particular attention is paid to integrable classical string models. So in his introductory remarks, and this is something I'll be reading some more later as I haven't really got into it very well yet. I feel that many modern day workers are somewhat embarrassed by any inference that the beginnings of their research can be traced back over a century, since the soliton of the Korteweg-de Vries equation and also the optical soliton were discovered in the output of numerical calculations. I felt for some time that it was only the lack of computers that kept our ancestors from discovering the more interesting aspects of soliton structure. George L. Lamb. The above comment concerns the beginnings of the soliton theory of completely integrable and nonlinear systems of PDEs, and could be illustrated by the following examples. So this is with regards to this idea of the soliton theory is like, well, PDEs aren't completely integrable in the nonlinear. These are. So, a soliton system with its integrability conditions for an auxiliary linear system in two or more independent variables. So it's like, how do we solve nonlinear things a lot of the time? Well, we reduce it to a linear thing. Vis-a-vis the analysis from algebraic geometry, where the idea is that these singular points and singularity theory is multiplicity theory and all this kind of come into these kinds of things for Fritz London's models of the extra classical. All right, well, this is to be considered quite a bit more later. It's very good. It's still being learned today, right? Since when these were conference proceedings of Scheveningen or wherever it was in the Netherlands, where that is. And so it's pretty remarkable that today that's just the latest, greatest thing. So then this is what I wanted to get to in for a while, was this in the path integral book. So this is Velasco's Fourier analysis and boundary value problems. And I forget quite where we left off, but the idea was to kind of carry on from this, because what it was getting into was here in this chapter 3, return to the heated bar, the steady state solution. And it gets into here that as we started reading this quite some time ago in descriptive differential dynamics and read it for quite a while, there was things like the Fourier style analysis, the Dirichlet kernel, the Feher kernel, the notions of Dirichlet after Riemann, and the notions of after the idea of the trapezoid rule, or when things always go from greater to lesser in concentration, and that being the part of the formalism of the problems for the Fourier style analysis of the transmission of heat through a uniform media, and the transmission of heat through spherical media, that these are the ideas that make for the Fourier style analysis what gets into, before we get into stuff like the Fourier transform. But as for the Fourier series, in the Fourier style analysis, that there's something to be said that Fourier style has two entirely different things going on, the Fourier series and the Fourier transform, with regards to then how they have as well the same kinds of things going on. With regards to the transform is just a separability equation in terms of distance and time, meters per second or seconds per meter. And whereas with the Fourier style, the Fourier series is with regards to trigonometric or otherwise periodic functions that make it so that an infinite series of those at the left and right hand side can be found the coefficients of the infinite series that results reconstructing a value as if it is of this thing. So that's just something that has been kind of reached here in this approach so far. From this great book of Velasco. And so what I wanted to kind of look at, I wanted to look for some more of the historical ideas. So we're talking about the existence of both the steady state and the transient solutions. So this basically reflects on the globally stable and locally stable, or the stable and astable, and these kinds of things. About where the hypotheses are applicable, and about the uniqueness and continuous dependence on initial and boundary values, when those can be proved. He quotes this on his own work, The Uniqueness and Stability of Solutions for a Type of Parabolic Boundary Value Problems, from the International Journal of Mathematics and Mathematical Science, 1989. That I wanted to just kind of look at this again for a while, where it gets into things like time-dependent problems. And so the other book I wanted to look at some more was the reading from about the path integral and development of the extra classical line integral with regards to particle wave duality, and then here the transmission of heat. Because they both kind of, from the early parts of the readings, there was a great amount of value derived from, for example, in the reading from the path integral about the time ordering property, and here from reading about the Fourier style analysis, just a good refresher or an introduction to what goes into the usual models of propagation of things according to a gradient that is so established according to the flow of these things, in terms of when things either flow as of the superfluid, or flow as of the barely fluid, or that which either has what you'd think of it as like a zero surface tension, immediately just falls all away, vis-a-vis an infinite surface tension, barely moves at all. With regards to that somewhere in the middle are quantities or result systems like heat, in terms of that being magmatic, that was the idea that was kind of like wax or magma, not having infinite surface tension, but not having zero either, holding it together. That's the thing. So section 3.11 here says time-dependent problems. The last heat problem ever studied by Fourier in December of 1828 was that of a bar whose endpoint temperatures depend on time. So he's introducing some dynamics into it. And then otherwise these quantities are kind of the ones we already were using before. We shall consider now a more general situation in which both the rate of internal heat generation and the endpoint conditions depend on time. That is a boundary value problem with the form C u sub 1 equals K u sub x plus Q of x sub t in D. And then the next one is A sub 1 of u of 0 comma t minus B sub 1 of u sub x of 0 comma t equals G sub t. So that there's just framing it, the difference of the value of 1 to its partial is equal to this end of it here, for t greater than 0. And again, giving kind of the t greater than 0 is like t greater than 0, so 1 over it is never negative infinity or something like that. It's always positive. And then about the windowing and boxing things, and about when you have natural units and whether they're the maximum also, and these kinds of things that get into all this algebraic setting of the arithmetic setting, the geometrical setting. Here is with regards especially to the great term mentioned, geometrization, which is when you make a model, it's like, well, what's your model like? It's like geometry. I was like, great, then everything applies to it that applies to geometry. And then the second condition, pretty much same as the first, except for A, the other and. 0, x comma 0 equals f of x for x between 0 and A inclusive, where in addition to the usual hypotheses, is 1, that A1, A2, B1, and B2 are non-negative, 2, that A1 plus B1 greater than 0, and A2 plus B2 greater than 0, and 3, if A1 equals A2 equals 0, then G equals H are on the order of 0, and Q is on the order of 0. So by adding these usual hypotheses, these help both define and derive what can be, givens in the course of it, and then also they remain to not be contradicted, and so they have to be checked out both ways, that they're both not contradicted, and that they're satisfied, and that it's sensible what results from so supposing them. So kind of these three different ways. And it reminds me the other day I was using one of these chat machines or one of the great new online assistants. And so I was curious how to interpret some mathematical results that are counterintuitive. And so I fed it the usual, these kinds of setups, and it provided the usual intuitive, but wrong or incomplete type of thing. So I just prompted it with some of these extra hypotheses, and it turned itself quite directly around. So it's pretty intuitive, a general model of cognition's view of these things. And the idea is to make it so for everybody else too, because I'm no great mathematician. I mean, for a person, I'm more than usual, and I'm a great mathematician, but trying to figure out how to do that in the applied and over time is really its own sort of practice. And especially when I spent most of my time, dealing with zeros and ones and true and false in computers, which is really something that I've studied a lot, know a lot about. We shall assume that G and H are non-negative differentiable functions, and that F is non-negative, is continuous, has a piecewise continuous derivative, and satisfies A sub 1 F 0 minus B sub 1 F prime 0 equals G sub 0, and A sub 2 F A plus B sub 2 F prime A equals H 0. So it's just building up that for these, the other ones are differences, these are sums. Or is this so for like so, the other hypotheses and conditions that we have then. In view of the third hypothesis, the case A1 equals A2 equals 0 is actually time independent and has already been considered. Therefore, we assume that A1 plus A2 is greater than 0. And the first thing to note is that there is no such thing as a steady state solution because the whole situation is dependent on time. However, it is still possible to reduce this problem to one with linear endpoint conditions if we find a function u of x and t that satisfies the given ones. For then the function v equals u minus big U would satisfy the same type of problem, but with g on the order of h on the order of 0. The simplest approach is to investigate whether or not a function of the form u x sub t equals a sub t x plus b sub t would do the job. Indeed, such a function is easily found by substitution of this expression in the given endpoint conditions. This gives two equations from which the unknown functions a and b are readily obtained. result is u of x sub t equals this quantity a sub 1 ht minus a sub 2 gt over this quantity a sub 1 plus b sub 1 that times a sub 2 plus a sub 1 b sub 2, all that x plus this quantity b sub 1 ht plus this quantity a sub 2 plus b sub 2, all that g sub t over this quantity a plus a sub 1 plus b sub 1 a2 plus a sub 1 b2. Now I'm not sure why they didn't factor the denominator out, or rather left it in, with regards to those two being the same for the left-hand side, right-hand side. So, and then as with regards to that, it could kind of be written 1 over this quantity, you know, a sub 1 plus b sub 1, that quantity, a2 plus a1, b2. All that times, otherwise how that's factored out. But to continue, it should be no surprise that when q is on the order of 0 and kappa is on the order of 1 and g and h are constant, big U becomes the steady state solution. They have 3.8, which would already have been read off. It goes in some more about it and then just goes into sort of usual development. Our question now, inspired by Lagrange's method of variation of constants, is whether or not our problem has a solution of this form that's a sum of these unknown functions rather than constants. The advantage of this type of series is that if it converges, it automatically satisfies. So this is there's much more to be gotten into in this, with the idea of extracting again out kind of the methods of these ideas about then how to make it so how it's possible to make for these usual derivations to build up what happens in their generalized inverses for their complementary duals when trying to figure out for meters per second or seconds per meter for moment in motion what these things are going to have to do with respect to each other to reflect each other to make it so that there's a usual general way to help sort of support solving a wider class of these systems. Sturm-Liouville, meet Riesz-Fischer. Frigyes Riesz posed himself inspired by the work of Hilbert and Schmidt. In view of Bessel's inequality, Riesz posed his question as follows. Given a complete orthogonal system of the phi sub n's and a sequence of constants c sub n such that the sum of n from 1 to infinity of c squared n times the norm of phi squared or phi n squared converges, is there an integrable function f whose Fourier conventions are the Cn? Let us state at the outset that the space of all Riemann integrable functions is not large enough to provide an affirmative answer to the preceding question. This we shall prove later. So this gets into the the spaces of the spaces of the spaces of the functions. Then for like all the spaces of the terms, the spaces of the functions upon them, kind of like, well, it's like how big is the dictionary? I was like, well, does it have all the sentences ever written in the world in it? No, it's just got words. So with the ideas of these elements and their spaces, and then the spaces in their spaces, of the functions in their spaces, make for all such matters of relation, helping explain why arithmetic and algebra and geometry and function theory and topology all make for one kind of geometry. And this kind of stuff helps to kind of level the boat that is everything in it in mathematics. That there is one. All right, so yeah, this is where I want to continue reading. I was getting a lot of value from reading this linear narrative from Velasco, who then goes on to describe, it can be shown that the orthogonal system of this has the Parseval property and is therefore complete, and then the Fourier-Bessel series converges in the mean. For pointwise convergence, the following result, first stated by Fourier, later proved by Hankel, and independent by Schläfli, using the theory of residues, introducing interesting things and who did them to help provide points of reference to go find out what and how they did it or what they might have been thinking. The first proofs without the use of complex analysis were provided by Kneser and by Hobson. beyond the scope of this book. Sometimes beyond the scope of this book is like, it's just a wealth of detail that is beyond the scope of this book. And other times, beyond the scope of this book is like, I can't tell you anything about that in this book except briefly mention it, because otherwise I would be in the scope of their book. Gauss's corollary of the Ostrogradsky Gauss theorem. It's a lot easier to find a theorem when it says Ostrogradsky than Gauss. Poisson, Gauss, basically the two most often found names in the discrete and continuous, or in the complex in that case. Dini-Bessel. See, here's Dini again. We're just talking about Dini with regards to Dini and Beltrami. This is about Schläfli classes and a Christoffel tensor. And the Chladni functions, which are those drum functions that show that they're minimums. Consider now the solution of the Dirichlet problem. All right. Nicolas and Basset, who proposed certain types of this Bessel equation, modified Bessel equation of order P, in a study of the catenary. It was a treatise on hydrodynamics of 1888, which Alfred Basset introduced this solution of form and notation about Bessel functions and negative powers of the imaginary modified Bessel function. We should say in passing that Basset was not concerned with the Dirichlet problem in a cylinder, but rather with more sophisticated applications, such as, for example, the study of the rotational motion of a liquid in a closed vessel bounded by two coaxial circular cylinders, a topic that we cannot explore here. Well, Maclaurin series, Poisson's integral. Bessel's integral form, Fourier cosine, Fourier transform. So in the Fourier style, then in and after this for these types of differential equations, and in the book it's called Fourier analysis and boundary value problems, is to get into a lot of these different kinds of things. In the previous section, we defined the delta function as a linear functional, that is a real valued linear functional whose domain is a certain space of ordinary functions. We did not describe this space. It turns out that it's both convenient and sufficient to define these functionals on a space of the very smooth ordinary functions called test functions, precisely defined as follows. Well, that's what we kind of got into today. What I'm going to kind of take a look at that is more of this later. I'm reading back about the path integral. Good afternoon. Have a great day. Meters per second or seconds per meter.